This is chapter 10, Thermal Properties of Matter. For this chapter, we're going to look at what is internal energy and what are the changes of state and the boiling and evaporation. So first, what is internal energy? Internal energy refers to the total microscopic energies of the particles in the substance, and this is made out of the kinetic energy and the potential energy of the particles or molecules. So the kinetic energy is due to the motion of molecules. We're not talking about the entire object, we're just talking about the individual molecules, and this Ke is proportional to temperature. Then potential energy, the Pe, is due to the intermolecular forces of attraction between the molecules, and this is related to the change in state. So please take note, this Ke and Pe are very different from the Ke of the entire object or the GPe. Now, when a solid is being heated up, when the temperature of a solid increases, the Ke of the molecules will increase. Because it remains as a solid, there is no change in Pe, and internal energy, which is Ke plus Pe, it will increase. During melting occurs at a constant temperature, so there is no change in the Ke. But because the substance has changed from a solid to a liquid, the Pe has increased. Therefore, the internal energy has also increased. When the liquid is heated up, the temperature of the liquid increases, so the Ke will increase. It remains as a liquid, so there is no change in Pe. During boiling occurs at a constant temperature, so there is no change in Ke, and due to the change in state, the Pe will increase. When the gas is heated up, the temperature of the gas increases, so Ke will increase. It remains a gas, so there is no change in Pe. Now let's look at a heating curve. A solid being heated up, melting to becomes a liquid, boils to become a gas. So what is melting? Melting refers to a change in state from a solid to a liquid at the melting point. For boiling refers to a change of state from a liquid to a gas at its boiling point. Now the temperature during melting and boiling remains constant because the thermal energy is absorbed to break intermolecular forces of attraction. There is no change in the Ke of the molecules, and therefore no change in temperature. Now let's look at a cooling curve. A gas condenses to become a liquid and freezes or solidifies to become a solid. Now condensation is the change in state from a gas to a liquid at its condensation point. Freezing or solidification is the change in state from a liquid to a solid at its freezing point. Similarly, temperature is constant because thermal energy is released when the molecules form stronger intermolecular forces of attraction. So again, there is no change in Ke of the molecules, and therefore no change in temperature. Now, evaporation refers to a change in state from liquid to gas at any temperature below boiling point. So if you have a beaker of water or cup of water, what's happening is that the water molecules are always moving. They are in constant random motion. So they will collide with each other, and some collisions will cause the water molecules to have more energy. Some collisions will cause them to have less energy. Now, when the water molecules have sufficient energy, they can overcome the attractive forces of attraction and they can overcome the atmospheric pressure. Such molecules will have enough energy to escape from the surface of the liquid into the atmosphere. So that is evaporation. So the energetic molecules will leave the the water. So what's left behind are the less energetic water molecules, and this causes the average Ke of the molecules to decrease, and because of that the temperature of the liquid will decrease. So this is what we call the cooling effect of the liquid. Cooling effect due to evaporation. So a person will feel cold after swimming because of this cooling effect. When the water on the swimmers or on the person evaporates, then thermal energy is then transferred from the warm body to the cooler water. Therefore, the person feels cold. Now, there are many factors that affect the rate of evaporation. For example, temperature, humidity, surface area, atmospheric pressure, boiling point of the liquid, and wind. Now, there are differences between evaporation and boiling. Boiling occurs only at boiling point. It is a fixed temperature, while evaporation occurs at any temperature below boiling point. Boiling is a relatively fast process, while evaporation is a slow process. Boiling takes place throughout the liquid and bubbles are formed, but for evaporation only takes place at the surface of the liquid and no bubbles are formed. Now, boiling of course doesn't produce a cooling effect, but evaporation has a cooling effect. Let's do some practice question. A pure substance has a melting point of 50 degrees Celsius, and the substance is cooled from 80 degrees Celsius to 30 degrees Celsius. Sketch a graph to show how the temperature of the substance changes with time as it cools from 80 degrees Celsius to 30 degrees Celsius. So at time 0, we're going to start off at 80 degrees Celsius. Then as it cools, it will reach the melting point or the freezing point of 50 degrees Celsius. And after that, it will continue to cool and become a solid, and then at 30 degrees it's going to maintain its temperature. Alright, so a few things to take note here. Number one, there will be a change of state at 50 degrees and a maintaining of the temperature at 30 degrees Celsius. Now, if possible, if you have to draw this change in temperature to be a steeper gradient and the other one to be a gentler gradient. Part B, describe the changes, if any, that occurs to the arrangement and to the motion of the molecules of the substance as it cools from 80 degrees Celsius to 51 degrees Celsius. So between 80 degrees Celsius to 51 degrees Celsius, the substance remains a liquid. So, substance remains a liquid when temperature decreases. There is no change to the packed close together and random arrangement in the liquid. However, for the motion, the average speed of the molecules will decrease when the temperature decreases. Now, what happens when it freezes at 50 degrees Celsius? It changes from a liquid to a solid. So at freezing point, the substance changes state from liquid to solid. Arrangement changes from irregular arrangement packed close together to regular arrangement and closely packed. In terms of motion, there is no change in the average speed of the molecules because the temperature remains constant at 50 degrees Celsius. However, the molecule changes from sliding past each other to vibrating about fixed positions. Let's try the second question. A liquid at a temperature of 100 degrees Celsius is placed in a test tube. The sample is allowed to cool for 120 seconds in a laboratory where the temperature is 20 degrees Celsius. Figure 1 shows the cooling curve obtained. State the time when the sample becomes completely solid. So in this question, we start off with having a liquid. And when cooling continues to occur, the first solid will appear. And we will see liquids and solids appearing. And right at the end, the last liquid will disappear and it becomes a solid. So at what time does the sample becomes completely solid? At 95 seconds. Okay, over here. Part B, state why the sample is losing thermal energy throughout the experiment. So the temperature of the sample is from 100 degrees Celsius to 70 degrees Celsius, and this temperature is consistently above the laboratory temperature of 20 degrees Celsius. And since thermal energy always flows from a higher temperature to a lower temperature, the sample is losing thermal energy throughout the experiment. In part C, explain why the temperature of the sample is constant for some of the time, even though thermal energy is lost to the laboratory. So between 30 to 35 seconds, the sample is freezing. So thermal energy is released when the molecules come closer and form stronger intermolecular forces of attraction. There is no change in the average Ke of the molecules, and therefore there is no change in temperature. In part D, a test tube containing an identical sample of the liquid at 100 degrees Celsius is placed in a beaker of water that is kept at a temperature of 90 degrees Celsius. Sketch the cooling curve obtained. So we're going to start again at 100 degrees Celsius, and we're going to end at 90 degrees Celsius because that is the temperature of the water. So we're going to get a curve, and it will plateau or flatten out at 90 degrees Celsius. We will expect a gentler curve because the rate of heat transfer is slower, and it will flatten out at 90 degrees Celsius. Let's look at question 3. A large cotton sheet and a small cotton sheet are hung out to dry as shown. The sheets are dry when the liquid water in them has been changed to vapor. Part A. State one reason why the liquid changes to vapor by the process of evaporation rather than by boiling. So over here in this example, the sheets are at room temperature, so the water is at room temperature and not at boiling point. Therefore, evaporation occurs. For the sheets shown, state and explain from which sheet evaporation occurs at the greater rate. Now, the rate of evaporation is proportional to the exposed surface area of the liquid. The larger the sheet, the larger the surface area, then evaporation will tend to occur faster. Therefore, evaporation will occur at a greater rate on the larger sheet. Part C, state how the rate of evaporation from the large sheet changes when the temperature decreases. Use your knowledge of molecular motion to explain why this happens. Now you have to talk about water molecules in your answer. So when temperature decreases, the average Ke of the water molecules decreases. So less number of water molecules will have sufficient Ke to overcome the intermolecular forces of attraction between the water molecules and to overcome atmospheric pressure. Therefore, the rate of evaporation will decrease when temperature decreases.